Energy plays a central and key role in chemistry. Energy is involved when a bird flies, a bomb explodes, rain falls from the sky, and when electricity flows through a wire. Energy is all around you. You can hear energy as sound, you can see energy as light, and you can feel energy as wind. You use energy when you hit a softball, when you lift up a book bag, or when you compress a spring. If energy is involved in so many things and so important in chemistry, what is energy? Energy can be defined as the ability to do work. If an object or organism does work, meaning that it exerts a force over a distance to move an object, the object or organism uses energy. So we defined energy as the ability to do work. And we define work as exerting a force over a distance to move an object. So what do we mean by that? If this was an object and a force was pressed on it, and that force moved the object a certain distance, that would be work. Because of the direct connection between energy and work, energy is measured in the same units as work, which has a joule unit. We defined energy as the ability to do work, and we define work as a force that it moves an object to a distance, or we could use the equation W equals F times D, W being work and F being force and D being distance. So another way to write that, force times distance, is what is called a joule. 1 joule equals Newton meter. And if we take this and plug in a Newton for force and a meter for the distance, then we have the definition of work. So a brief summary, we said that energy was the ability to do work. We described work as a force that pushes an object over a distance, or a force times distance. So we could rewrite this as energy is a force times distance. We took the joule unit, 1 joule equals 1 Newton meter, where the Newton force would be plugged into F, and the meter would be plugged into the distance. So using that, we would have energy could be measured in Newton meters. And 1 Newton meter equals 1 joule. And we could rewrite this as energy is equal to joules, or can be measured in joules. In addition to using energy to do work, objects can gain energy because work is being done to them. For example, if we had an object at the bottom of a ramp and a force was applied to the object, moving it a distance to reach the top, we could say energy was used on the object. And energy was added to the object when it went from one height to another height through what is called gravitational energy. The 5 main forms of energy are heat energy, chemical energy, electromagnetic energy, nuclear energy, and mechanical energy. The internal motion of an atom is called heat energy because moving particles produce heat. Heat energy can be produced by friction. Heat energy causes changes in temperature and phase of any form of atom. Chemical energy is required to bond atoms together, and when bonds are broken, energy is released. Fuel and food are forms of stored chemical energy. Power lines carry electromagnetic energy into your home in the form of electricity. Light is a form of electromagnetic energy. Each color of light represents a different amount of electromagnetic energy. Electromagnetic energy is also carried in X-rays, radio waves, and laser light. The nucleus of an atom is a source of nuclear energy. When a nucleus splits, also called fission, nuclear energy is released in the form of heat energy and light energy. Nuclear energy is also released when nuclei collide at high speeds and join, which is called fuse. The sun's energy is produced from a nuclear fusion reaction in which hydrogen nuclei fuse to form helium nuclei. Nuclear energy is the most concentrated form of energy. When work is done to an object, it acquires energy. The energy it acquires is known as mechanical energy. When you kick a football, you give mechanical energy to the football to make it move. Energy can change from one form to another. Changes in the form of energy are called energy conversions. It is important to realize that some of the science we stand on today was done by scientists hundreds of years ago, and what may seem like a small paragraph in a textbook or a simple concept could have taken a lifetime for the scientists to map out. This is why some chemistry concepts are described in such archaic frameworks. Scientists describe the world around them as it was, and built from tried and true studies. Energy conversions can help close the gap between work done hundreds of years ago and work that is being done today. All forms of energy can be converted into other forms. The sun's energy through solar cells can be converted directly into electricity. Green plants convert the sun's energy, which is electromagnetic, into starches and sugars, which is chemical energy. In an automobile engine, fuel is burned to convert chemical energy into heat energy. The heat energy is then changed into mechanical energy. An energy state is energy with specific conditions that is often described relatively. Relatively meaning compared to something else, usually described as energy that is higher or lower. The most common energy conversion is the conversion between potential and kinetic energy. All forms of energy can be in either of two states, potential or kinetic. Kinetic energy is the energy of motion. Potential energy is stored energy. The equation for kinetic energy is Ke equals m for mass times v squared for velocity squared divided by 2. So looking at the equation, what has a greater effect on kinetic energy, mass or velocity, and why? We had two variables, m for mass and v for velocity. Velocity has an exponent right here. This means that velocity would have a much greater effect on kinetic energy than mass. Potential energy is stored energy, stored chemically in fuel, the nucleus of an atom, and in foods, or because of the work done on it. Examples of this would be stretching a rubber band, winding a watch, pulling back a bow's arrow, or lifting a brick high in the air. Potential energy that is dependent on height is called gravitational potential energy. Energy that is stored due to being stretched or compressed is called elastic potential energy. Roller coasters work because of the energy that is built into the system. Initially, the car is pulled mechanically up the tall hill, giving them a great deal of potential energy. From that point, the conversion between potential and kinetic energy powers the car through the entire ride. So when we look at this cartoon, we can see that when the cart is at the top of the roller coaster, it has the most potential energy, and when it's at the bottom of the hill, it has the most kinetic energy. As the cart goes down the hill, the potential energy decreases and the kinetic energy increases. And as it goes up the hill, the potential energy increases and the kinetic energy decreases. Looking at a common everyday event, as a basketball player throws a ball into the air, various energy conversions take place. The law of conservation of energy is an important law to grasp and understand when studying chemistry. The law of conservation of energy says that energy can neither be created nor destroyed by ordinary means. An example of something that is not ordinary would be a nuclear bomb. This law says that energy can only be converted from one form to another. An example of this was with potential and kinetic energy. When we described this with the roller coaster, the cart had more potential energy at the top of the hill, and as it went to the bottom of the hill, the potential energy decreased and the kinetic energy increased. So the energy was not lost, it converted from one form to another. If energy does seem to disappear, scientists look for it, leading to many important discoveries. It was mentioned that the law of conservation of energy was true under ordinary means, hinting there is something more to the story, and there is. Under certain extraordinary circumstances, such as those involving a nuclear reaction or high-speed particles, energy can indeed be converted into mass, and mass can be converted back into energy. In 1905, Albert Einstein said that mass and energy can be converted into each other. He showed that if matter is destroyed, energy is created, and if energy is destroyed, mass is created. This was under his famous equation, E equals mc squared.